My second slide is about a 2-month-old comment in Nature, which says the small drone revolution is coming. And China considers itself as a leader in the world on low altitude economy, as they call, and they spend over $200 billion this year. And in 2023, the whole Hungary GDP was of the same amount of money. So this talk will be about drones. We start with a few general comments. What are the major aspects of many drones moving around? We would like them to be able to move together also, just to flock, because it's one of our field to study things moving together. They also have to avoid obstacles, obviously, like buildings. And if there are many drones, and they have particular destinations, we have a traffic situation. It's not a very common topic, but it is going to become very relevant in the near future. Okay, but how to do it? It is not so trivial at all, and in fact, there is no other option in the case of drones than decentralized control. For that, we need autonomous drones, which are not so common. In the news, there is a lot about drones, unfortunately, in the context of the wars. But those drones are first-person view drones. So someone from a distance controls the drone. So it's unmanned, but in fact, a man controls it. And of course, there is something in between. The drones can have a hierarchical priority system among themselves. We started studying drones in 2008. And it might be something surprising to you, but there were no drones available in 2008 on the market. This is so recent and so just shooting up. So we didn't start to work on drones. We worked on collective motion, and I wanted to study collective motion in 3D experimentally. And for that, we attached to the back of pigeons GPS devices. At that time, they were so big that it had to be a backpack. Now what you see is the actual GPS data twice as fast as they occur of a flock of 30 pigeons in a later stage of our investigation around 2012. Look, the almost instantaneous collective decision-making about the direction of flight, even whether it's counterclockwise or clockwise. This was amazing. So we wanted to understand. First, we were happy to study. We published the observations, the data, but then we decided we really would like to understand what may go on in their minds, but how this decision-making process occurs. So I had a proposal to Europe, a successful proposal about simulating pigeons using aerial robots. At that time, the drone was an uncommon word. So these had to be autonomous because birds are autonomous. They make the decisions themselves. So if we are using autonomous drones, then we can have an insight into how they can organize their flight, which is both orderly and changing in time. We had to build these smart drones, which are not as cute and small. And some of the recent drones, they had a large brain with a computer, with all sorts of interfaces, interacting through sending their GPS coordinates by Wi-Fi to each other. This was an interesting development, but of course, we also had to program their brains, to find the rules, the interactions they eventually have to consider to operate as a flocking bird, as a flock of birds. So for this, we needed real-time communication among drones. There is no simple set of rules. Very recent, I don't have a slide about it, publication shows the brain of a fruit fly. In fact, 15 neurons in a fruit fly's brain. It is amazingly complex, of course, much more complex. So the simple set of rules don't work. No, birds are very sophisticated. Why? Because there are significant delays, much longer delays in our electronics right now than in what birds have. The turbulent airflow, we have to avoid collisions. There are all sorts of other technological limitations, like acceleration cannot be arbitrary, turning angle cannot be arbitrary. So I have a video about the effect of delay. The delay of birds is much shorter than in the people because they're much smaller and they are tuned by nature to react very quickly. So this video shows how a lot of wild geese in Hungary are about to decide to take off. And you see, even with their extremely quick, very short delay time, all sorts of waves are produced. So these play important role. Now the way it works in the case of drones, we build a composition of all sorts of components of velocities which contribute to the desired velocity, to which I will return very quickly. So these terms here correspond to the fact that we want them to flock, we want them to repulse each other, so not to collide. There is a friction force, we assume, which is some kind of original contribution, and it will be discussed in the next slide. And of course, there are all sorts of other terms in the velocity which reflect that we don't want to bump into walls or obstacles. So the desired velocity for me came from our work with Dirk in 2000, where we were trying to simulate how people move in confined situations, especially when there is panic. because when there is panic, then the subtleties of human nature, human behavior don't play anymore much role. They just want to move in the preferable direction with the desired velocity. And there was this term here representing friction, which we introduced. Why? Because we had a few videos about panic in stadium. And look at this, they are trying to escape. There's a huge pressure. They just stop moving. They cannot move through the door because there is so much pressure from the others, and there is friction of the bodies. So the corresponding simulation, which we published in 2000 in Zurich, successfully encountered for this phenomenon, which apparently, results in a terrible situation. They just cannot move quickly enough outside of the room. And this simulation is a much larger scale than the before one. There are more exits, and the colors indicate the pressure what people are subject to in this situation. If you ever try to run, sometimes I have been called a few times during my career by people from a crowd experiencing extremely strongly fluctuating pressure on them. And they just justified this simulation, which shows this. Okay, so I cannot go into the many equations. As I said, the bird's brain is much more complicated than the system of equations we can describe for their behavior. We described these equations, applied these, and of course, even more one. This is just a visualization of the equations for acceleration, forces, friction, having a lot of parameters, in this sense, not being a very good modeling approach. But these parameters are not free because we know the kind of behavior we expect, we would like to see. And those behavior, we can optimize the parameters so that the observed behavior in the simulation looks like nature. So we went on with this, and included the role of obstacles, walls and obstacles. So these are not future cities, these are present day cities, but the future cities will look like this or even more like. So the drones are optimally flying around between 100, 200 meters high. Otherwise, they would interfere with other ways of aerial transport. So they have to get around this. Oh, of course, this is all much more complicated what we can simulate. Still, this very simple looking video shows not a simulations, but the group flight of drones. A bit reminiscent of those how birds, the flock of pigeons behaved. And this is what happens if you have a few obstacles. These are GPS coordinates defined regions which cannot be visited by these drones. So these are 30 drones. Their eventual flight visualized with the help of, it's a very rich, it's like already on this level, it is, not converging. It is like chaotic. They sometimes join, separate, and so on. It was much less easy than it looks to achieve this situation. Okay, so the final part will be about traffic. We are just arriving at traffic. Again, here, I don't go into the details of this figure, which is even more complex. The situation is much more complex than it looks. If there are several drones and they are trying to move in different, in the direction of different targets, conflicting targets, then collisions have to be avoided. And it turns out that you have to adjust the direction according to this, as you will see soon. There are all sorts of scenarios due to the many various situations of angles and number of drones potentially colliding. So we really had to calculate, estimate the risk of a collision for drones which follow our rules, and estimate the throughput. And here is the famous analog of a famous traffic throughput figures in the, this is still in a 2D at this point. And we introduced layers later to make use of 3 dimensions. A fully 3-dimensional modeling and experiments would have been just too difficult. Whereas in ordinary traffic, there is an optimal density, and at this density, there is a reasonable throughput at this density, and the collision risk is smaller than 1 million. It cannot be completely avoided due to noise and so on. So this is our simulation of our rules for 50 particles. The destinations are dedicated randomly, and it is very difficult to find an optimal way for these to move and not to collide. And as you see, also there is queuing at places. It's not, there are places where they cannot arrive because too many would go too close. So there's a queuing problem. And I hope you can see that the methodology works for 5,000 drones also. So it is a scalable approach. Okay, so what you see now, very close to the end of my talk, is, okay, let me see. Yes, this is not the simulation. It looks like the simulation, but it is the experiment we carried out. Okay, I'm sorry, at this point, this is still the simulation. Yes, this is in order to show you what happens if there are 2 layers, or there are 3 layers or 4 layers in the simulation. The distance they make between the layers is enhanced here so that you would see what happens. In fact, it is a time and energy consuming to make use of more than one layer. But with this, especially if there are 4 layers, then within a layer, there are much less potential conflicts anymore because they move to the east, everybody in average, or they move everybody in that layer in the west. That's why the average colors are different here. Colors code for, okay. So now comes what we are most proud of is our field experiment uh, about using 100 drones. And it is an amazing feeling, I tell you, just to hear the noise of these drones, because they are not very small, and there are many, as they just move up in the air. And okay, if
Thank you, Tamas. Could you wrap up your interesting talk slowly, please, so we can have discussion?
yeah, I go to this one, uh, uh, which shows how this is my last uh, slide. This is how it looks. This is how they move so smoothly, but each in the direction of their target. And this is our team 10 years ago.